Well, what's up, everybody? Welcome to Neuroscience. Let's think about what we're looking at here for one last lesson here in Neuroscience. This is a campfire in my woods, and I have the trees in the background there on purpose. Think about the sensation that you can probably recognize because I'm sure you've been around an open fire at some point. Can you get the idea that you'd feel heat coming off of this thing? Well, where does this heat come from? Like, where's the energy from the heat? And like, I know fire. Like, you can just say fire, right? But let's take it a tiny bit deeper. Like, how does that even work? Like the rock doesn't burn. What is it about the wood, the tree, that allows it to burn and give off heat energy? If you've ever heard the old saying, thermodynamics saying, energy is never created or destroyed, this fire isn't creating energy. It's taking energy from one of these trees, and these trees have been cut down right here in this woodlot. And we'll close this down. And giving off that energy, right? So what we're going to get into here is a fairly complicated idea, which is the carbon cycle. So we'll write that up here. The carbon. All right. And it's complicated because it's really going to require little bits of all the earth science we've done all year round. So let's start with going way back to when this planet formed 4.6 billion years ago. Planet formed. If you remember that whole deal, it's out of a planetary nebula, which is that interstellar cloud of gas and dust that coalesced into the sun and all of the planets. And the one that we have, I mean, that's pretty much all of what we got so far. I mean, you and me, the stuff that's in us, the stuff that's in this computer screen, this mask. You had to have all of those elements at that point. Yeah, there's been some meteorites that have hit since then, but that's pretty much all of it was formed there, including all of the carbon we have. Okay. So there's like kind of the pieces are set now. It's like we begin with that. Then, and we talked about this the other day. I know this isn't going to exactly look like the right setting with a tree right next to a volcano and all the other stuff we got to do here. But there was the idea that when volcanoes go off, they give off a whole bunch of different gases, water among them, but CO2 being on that list. Ooh, look, they give me a subscript feature. Beautiful. Carbon dioxide being on that list of things that come out into the atmosphere. And that would be our early atmosphere. And hopefully you did that last lesson about the history of the atmosphere and the oceans. And yeah, water would be coming out of there, nitrogen would be coming out of there, methane, other things. But carbon dioxide is going to come out into the atmosphere at that point. Then there was those stromatolites, the cyanobacteria, that changed as a single cell organism, changed the nature of the atmosphere forever. Yes, a living thing can change the nature of the atmosphere, which is kind of what we're getting at today, by inhaling carbon dioxide and exhaling oxygen, similar to what trees do today. So going back to my campfire, what's the deal here? If we do a sun, let's throw a sun up here in the top corner. All right, the sun's rays hit leaves. And now the chemistry of this, maybe, depending on how last year went with COVID and all of that, the chemistry of this you should have done in living environment last year. That photosynthesis in trees helps them build their tissue. That's how they grow. That's their food, right? They take in carbon dioxide and they let out oxygen, which we like, right? But we like all these things in fairly specific proportions. We evolved to survive having these things in fairly specific proportions. And if you ever need to know those proportions, they're right here on the front page of the reference tables. How much is in the troposphere? 21% oxygen, 78% nitrogen, and 1% everything else. And those words are over here. So what's building this plant tissue is carbon. I mean, trees have a lot of carbon in them. And if it like this is getting into chemistry that I'm not great at, but I hope that you guys do it next year. building up carbon to hydrogen bonds is what like makes plant tissue, and then breaking them in a campfire is what produces the heat. So again, if we're tracing the flow of energy from the sun into the tree, building plant tissue, then I release that when I have a fire, right? So what I want to get at is the idea that if you've got a living tree, it's going to, throughout the course of its life, take in some CO2 and let out some O2. But all of the carbon dioxide that it takes in that it builds plant tissue with, we could consider a carbon sink in the short term. It absorbs carbon. One of the plans to fight climate change is to plant an enormous amount of trees. And that will do a good job for a while. But what you got to think of is what's the fate of these trees in the end? If I go cut it down, chop it into chunks, have a campfire, let's have a campfire. That's what a campfire looks like. What that's going to do with those logs is send out all of the carbon dioxide that tree brought in. Now, that's good in a sense. I heat my house primarily with firewood. And I'd say, other than the little bit of gas I use in the chainsaw, which doesn't come to much, it's a carbon neutral way of heating my house. Because all of the carbon that I let back out when I burn it was absorbed by that tree throughout that tree's lifetime. So, what is the real idea of a carbon sink? Like, how do we get rid of carbon, And how does this lead to what we're doing today? Is what if a tree dies? Boom, death. If a tree dies in a swampy, boggy area, and gets layered and layered and layered, like how we talked about the formation of coal. Let me look up a quick Google image of that. All right, so these are like present day peat bogs. They're used as a source of fuel. Like Ireland is kind of famous for using them as sources of fuel. Um, but it would have been layer upon layer upon layer upon layer of dying plant material. And here's this guy here. So you cut it into logs, you dry it, and you can burn it much like firewood. It's not as efficient, and like the volume you got to get for a certain amount of like heat and warmth in your house is a lot more than it would be with wood. But there you go. That's what it is. And you can kind of see the layer upon layer upon layer upon layer upon layer here, right? So this would be a sink of carbon. If you've got a healthy one of these that keeps on developing, you're going to suck carbon out of the atmosphere, suck carbon out of the atmosphere, suck carbon out of the atmosphere. Now, these are going to be fairly young. These are going to be young to a geologist, right, on the scale of, tens to hundreds of thousands of years. What happens if we have these from way, 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 way back into the Paleozoic, a couple 100 million years ago? Let's go back to our notes. If you do this and it gets way, way, way deep within the earth, that's where all that carbon is going to be locked up. And again, in these carbon to hydrogen bonds, which I don't even know if I remember how to do these chemistry drawings. Go learn them next year and come back and tell me I'm wrong. Something like that, carbon to hydrogen. And that's energy, plain and simple. So here's the difference. If we go and we build an oil rig and we dig this up, there's a huge difference. And I asked you to think about this on the sedimentary lab. And some people did okay with it. It was a challenging question. Let me actually pull that one up too. Sorry for all these pauses. Hang in there. So I asked you this question back here. I said, here's a tree in my woods that we cut down. Okay. And again, yes, there's some fuel for the lawn tractor to pull it out of there and some fuel for the chainsaw to cut it up. But if this is the other reality, if this is what you're going to be doing if you're burning fossil fuels, and why do we call them fossil fuels? Maybe that name will make a little bit more sense right now. They're basically fossilized sources of carbon. They're going way back into Earth's history when the exact same situation happened. A tree grew, photosynthesis, built up carbon tissue, built up chemical energy, essentially, and carbon to hydrogen bonds, only now that got preserved. It got taken out of the atmosphere. Any carbon dioxide that was in the atmosphere back then is buried and sequestered, preserved. Now, it's valuable as an energy source, but what's the downside? If I go and I burn a tree today, where's my lab? If I go and I burn a tree today, I'm burning carbon dioxide that was already in the atmosphere presently. And again, it's carbon neutral. If I go and do this, and I dig down with a oil well of some type, and I extract that and I burn it, I'm releasing carbon dioxide that was pulled out of the atmosphere in the exact same fashion that this tree pulled out of the atmosphere, only this when it happened, say, 300 million years ago. And that's where the problem is. That's why there's an imbalance of carbon dioxide in the atmosphere today. We've taken all of the photosynthesis that has happened. You got to think of this almost as a big, like, battery. The sun's been bombarding the earth since it formed, right? 4.5 billion years ago. Once we got photosynthesis happening and we built up all this plant tissue, they've been storing that energy chemically and buried. And again, having pulled carbon dioxide out of the atmosphere, now we're working our tails off as humans to go find every bit of that, dig it up, and use it as fuel. And I know that it's like I drove to work. I'm not saying we all got to go back to just walking everywhere and not having any technology. We got to figure out ways to deal with this, though. But understanding the basic principles behind it, I think, could potentially help us get through some of the silly arguments that still happen based around this. All right, moral of the story: we've gone and dug up all of the fossilized energy and taken all of that carbon from all of the eras, and we're stuffing it back into the atmosphere at alarming rates. Carbon dioxide then acts as a greenhouse gas. Now, we did this way back in energy, but we might as well take a quick spin through it. That when the sun's energy, it travels right through the atmosphere fairly easily. Some of it might get bounced back out, but right. So some of it is going to make it. A lot of it's going to make it right to Earth's surface, and it heats up Earth's surface. And when it does that, it has a shorter wavelength. Do you remember all this? And when it lets it go, it has a longer wavelength. When the Earth cools back down and gives off its energy, that longer wavelength is easily trapped by CO2, methane, and water vapor. So the problem with this all is that if we go and we find every single available bit of chemically stored energy, burn it, release its CO2, we increase that amount of CO2. And we measurably have, we undeniably have added more carbon dioxide to the atmosphere and continue to, which is more efficient at holding onto Earth's radiated heat, which means that we slowly and progressively get a warmer and warmer and warmer climate. That's Earth science. I now pronounce you Earth scientists. Congratulations. And again, one more time, thanks for all your patience on this. I was going to do a short one question quiz on this. What do you think? Pass? Here's what it's going to be. It's going to be, did you watch that video? 10 points in the classwork. All right. I really appreciate it, folks. And next year, when we're having a normal year, come on by and play some board games, hang out, be maskless, sit facing each other instead of all the same direction. I really appreciate all your work. Peace.